Thanks for the invitation. I'll talk about algorithmic fairness, and in the title it was written in classification and regression, but I'll focus more on regression because for some reason I thought it's a 1-hour talk. So this will be based on two works, one with Christophe Denis, Mohamed Ebiri, Luca Onetto, Massimiliano Pontil, and the second one with Nicolas Schroeder. Hopefully I will cover three things. First, I will present a general fairness-aware learning setup. Most of the papers would follow with slight deviations, this type of this setup. Second, I will start focusing on the regression with demographic parity constraint, which I will introduce. And finally, I'll try to provide a quantification of risk and fairness trade-off when we measure fairness in terms of demographic parity. Okay, so fairness-aware learning, we essentially need to specify four things. First thing is we need to introduce a sensitive attribute. So in the classical supervised learning, we would have features and labels. The label Y is binary, it would be a classification problem. If Y is real, it will be a regression problem. But right now we also have a sensitive attribute which represents, for instance, our society. So we can think of X being CV of a candidate, S being gender, and Y salary that is paid to the candidate XS. Second thing that you need to introduce is the type of predictions that you allow. And usually people consider two things. One is called fairness through awareness. It is the case where we allow sensitive attribute S to enter explicitly in the functional form of the prediction. For instance, if S is a finite set, say 1 or 2, then we allow to construct a prediction for each group, for group 1 and for group 2. Second one is the fairness through unawareness. In this case, we are not allowed to choose different functions for different groups. And once we predict, we can see only the feature X without the sensitive attribute. Then we specify the risk. Very standard. So if it's a regression problem, we typically care about the standard squared loss, expected squared loss. If it's a classification problem, that's usually the probability of misclassification. So here I emphasize that Z depends on the context that you consider. If it's a fairness through awareness, then Z is the couple feature and the sensitive attribute. If it's fairness through unawareness, then Z is just X. This probability is the joint distribution of X and Sy. And the last one, what actually defines the fairness of our learning, is that you partition your prediction into two things. You call some prediction functions fair and other prediction functions are unfair. There are a lot of ways to introduce this dichotomy. So here I will present three more popular ones, but they're really low. So we can have a look at this. It's a book that has been still written, available online. First one is the demographic parity that I'm going mainly to talk today about. It asks for the prediction as the random variable to be statistically independent from the sensitive attribute S. So informally, you take the distribution of the prediction in the group 1, you take a distribution of the prediction in the group 2, and these two distributions should be the same. Then you say that this function F satisfies demographic parity. It can be equalized odds. In this case, it's also asked for the independence from the sensitive attribute, but right now conditionally on the actual outcome Y. For instance, if Y is a binary random variable, so it's a binary classification problem, and then F is also a binary prediction, so it's a classifier, then equalized odds reduces to equality of group-wise false positives and false negatives. The last one, also quite popular, is the group risk equality. You say that the function satisfies a group risk equality. If I look at the risk, so in this case it's a regression risk inside of the group little s, then this risk should be equal to the population risk when I look at all the features as a whole. So the goal is so I'm not going to present right now an exact goal, but vaguely it would be like this. We have observations which are triplets, CV, sensitive attribute, salary. We would like to construct a prediction rule, which is just a mapping like this in a data-driven manner, which has low risk. We care about risk, and it has low unfairness. Unfairness is it's some functional on your prediction which tries to quantify the amount of violation of the previous fairness constraints, one of them or a bunch of them. And within this paradigm, there are three main approaches that people typically consider. One of them is called fairness at training. Here we take our data, we typically construct some empirical risk, we introduce some measure of unfairness and make an empirical version of it, and we solve some risk minimization penalized by the unfairness. It can also be in a constrained version. So we start from the data and we try immediately solve the whole problem at once. Second one is data transformation. Here what we want to find the mapping from the feature space X to some potentially higher dimensional or maybe even infinite dimensional space where so that in the new space we lost all the information about sensitive attribute. So that the discrimination cannot happen as long as you observe only the data representation. And at this moment, what you're going to do is to use some standard algorithm, but on the transformed data. The last approach is the one that I'm going to mostly talk about. Is post-processing. Here, the idea is that we have already some prediction functions, say a classifier or some prediction as a regression function that we use, but we trained it without having in mind any fairness-oriented goals. So we know that it's a good prediction and gives us a good risk. We kind of don't want to get rid of it. We would like to change it somehow so that once we change it, it starts satisfying some fairness constraints. And hopefully we do not change it too much because the risk of this prediction is low. I'm going to mainly talk about the post-processing. So now, regression with demographic parity, just to wrap up, we have triplets XSY. Predictions that I will consider will be of this form. So it's functions that receive X and S. The risk is the expected squared loss, and the fairness constraint is demographic parity, which asks for the statistical independence of the prediction from the sensitive attribute. The first thing that's good to understand is that in case I do not care about any demographic parity, then the best prediction, at least in theory, that I can provide is to take a base rule, which is just a conditional expectation of y given XS. And it's important to understand, well, why is it unfair at all? And there are generally two sources or a combination of the two sources. The left plot, say, features X are univariate, so lives on the real line. This is my regression function, and on the left plot, it is independent from S. So f star x1 is equal to f star x2. Even though it is independent of S, but it is possible that the features have two different distributions within the groups. So the distribution of X in group 1 is this blue curve, and distribution of X in group 2 is that curve. In this case, the base rule is unfair because it pushes to the prediction space these two distributions, and in this case, it pushes to two different distributions. So it does not satisfy demographic parity constraint. Another situation is that the distribution of features is independent from the sensitive attribute. So we look at the CV, and it is independent of S, no matter which group we belong to. So it's just one density. But the base rule actually depends on S. So this is a prediction for second group, the Bayes prediction for the second group, and this is a prediction for the first group. Then we push forward same measure through two different functions, so which not always, but results in two different measures in this case. So Bayes rule doesn't have to be fair, and most of the time both effects will happen, that we will have two different distributions of features and groups and two different prediction or optimal prediction functions and two different. Then what we can define is optimal fair prediction, which minimizes the risk under the constraint that the prediction is statistically independent of S. The very natural question that one asks is there a link between F star 0 and the Bayes optimal prediction? Just minimizes the squared risk. So in particular, assume I know the whole distribution of my data, x, s, y, then what can I do? Can I do something better than just minimizing the risk under the constraint? The answer to this question is yes, well, under some assumptions. If we assume that this random variable, the Bayes predictor within each group is a non-atomic random variable with finite second moment, then we can say at least two things. First one is that the distribution of the optimal fair prediction is precisely Wasserstein 2 barycenter of the group-wise distributions of the Bayes predictor. That's the first thing. So the good news is that we at least know the distribution that we would like to obtain from the optimal fair predictor. And the second one, once you know a distribution, you can just transport each measure like this to the barycenter, and that will give you a closed form expression for F star 0, which is given like this. So don't worry if you cannot parse it fast. There will be an example. This part is the transport map from this distribution to the barycenter, where F star S equal to little s is the cumulative distribution function of the prediction within the group little s, and F minus 1 is the quantile function, or just the inverse of the cumulative distribution function. There is a very simple interpretation of this expression for the case when S is equal to 1 and 2, so it's a binary protected attribute. For instance, imagine some new point comes to us, little x and 1, and we would like to understand what is the optimal fair prediction for this point. Rewriting the previous expression, we understand that it's just a convex combination of the Bayes prediction, F star x1, and something. So, and this something is determined following a very simple rule. The rule is like this: we plot two densities. The blue one corresponds to the optimal prediction, Bayes prediction within the group 1, and the Bayes prediction within the group 2. We put a line F star x1, and we compute an area under this curve, under this region. So area under this region is precisely this part of this expression. After this, we need to apply quantile function, but quantile function of the second group. It amounts to find a new point, so that the area under the orange region is the same as the area under the blue region. And eventually, the fair optimal prediction is just the convex combination of these two. It will be given like this. The nice interpretation of this is that if you are an individual X from group 1 and you get and your salary is higher than 80% of other individuals in the group 1, so the area here is 0.8, then the fair optimal prediction will put you somewhere so that in the population there will be 80% of total individuals having salary less or equal than yours. And the same works for the group X equal to 2. So it partially preserves the ordering within the groups. Based on this expression, what you can do, you can also propose an estimator, a post-processing one. So assume we have a data. Just for simplicity, I assume that we can sample features from each group. Also for simplicity, I'm assuming that it's an even number. And I have some base prediction I've had. And the only thing that I'm asking is that this prediction is independent from this unlabeled data. Then you construct a straightforward plugin estimator in this form, essentially by estimating all the quantities that you do not know and replacing f star by f hat. The only kind of subtle, well, there are two subtleties here, is that to estimate the cumulative distribution function and the quantile function, we use two independent sets. So since it's even, we separate it in two. One part is used to estimate the quantile function, and the other part is used to estimate the cumulative distribution function. And also we are adding these variables XCIS, which are random variables coming from a continuous distribution. They are independent from the data and from each other. And the reason to introduce it is that inside of this function, so it's not a continuous function, it's just a step function, but we want that this function doesn't have jumps larger than 1 over ns almost surely. For instance, f hat can be, say, knn, then most likely there will be some regions where the prediction is the same. So we jitter a little bit this prediction. Since it's coming from a continuous distribution, then there are no ties among these random variables. Then we can prove the following result. First one is the fairness guarantee, saying that for any joint distribution of the XSY, so we don't put any assumptions there. Any base estimator f hat, the only assumption that we put in it that this f hat is independent from the unlabeled data that are used to construct quantile function estimators of quantile function and cumulative distribution functions. Then f hat 0 that was introduced in the previous slide satisfies two guarantees. It is important to understand what is the spin, the first guarantee. This probability is with respect to the completely all the randomness inside of this f hat. And this is why we are able to get a bound which is of order 1 over capital N. So it's a very, very fast rate. But it's not extremely useful maybe in practice, because in practice what you want is this kind of bound where you first construct f hat 0, then you condition on the data, look at the violation, look at the discrepancy between two distributions, and then you average it. In this case, the rate is a standard parametric rate, 1 over square root of n. For instance, this bound can be made with high probability quite easily, but this bound only holds like this, the way it's written, where this expectation is essentially inside of the absolute value. Now, the good thing about this bound that we don't care about anything. We post-process f hat by f0, and these are the guarantees that it satisfies. For the risk guarantee, we need an assumption, and relatively strong. First thing, we assume that this distribution has a density with respect to the Lebesgue measure, but this one we already assumed to derive f star 0. Then we assume that this density is upper bounded. That's also not too bad. But also we assume that this density is lower bounded, and this is quite strong assumption, but there are certainly distributions that satisfy it, but need to be aware this assumption is relatively strong. Nevertheless, under this assumption and choosing these perturbations from uniform on 0, 1 over square root of n of order, then the estimation error of f hat 0 of f star 0 by f hat 0 is upper bounded by the quality of your base estimator. So that's just the estimation error of f star by f hat, and the price that you pay for estimation of cumulative distribution functions and quantiles. For instance, if you have really a lot of unlabeled data, this term disappears, and this bounty says to you that the post-processing that you apply will approximate the fair optimal prediction, as well as the initial base estimator approximates the base rule. So there are these two bounds which are nice, but here they were very rough, because we talked only about exact demographic parity. We did not really allow any deviations from it. And in the work with Nicolas Schroeder, we decided to look to some ways to relax this demographic parity. The question is, of course, which unfairness measure to use, so what kind of functional to introduce. And once we manage to introduce it, the other question is that if we fix some level of unfairness that we allow, what kind of risks that we can achieve. Before people already addressed this question, they said that, oh, let us measure unfairness by the distance between the distribution of the prediction within a group, say little s, and the distribution of the prediction as total, and we do not condition on any group. For instance, they consider Kolmogorov distance, total variation, or Kullback-Leibler, or in general any F divergence. The problem with this is that it's not really directly connected to the risk, and so you can do some stuff, but eventually, in order to precisely quantify the trade-off between risk and fairness, you need to do experiments, and you cannot really derive theoretically what are the trade-offs that are admissible. What we decided to introduce is a functional U of f, which is defined as the objective function, is the value of the minimum of the objective function of Wasserstein barycenters. So we look at the distance between the distributions of the predictions within each different group to the barycenter in the sense of Wasserstein 2 distance. The main reason to consider it is because of the previous result that I presented there, but I did not present it in this form. But it can be written so that the minimum over the risk, it's not exactly the risk, because instead of in the risk, instead of f star there is y, but they are equivalent. The minimum of the risk under the demographic parity constraint is equal precisely to the unfairness of the base prediction. But the hope is that this measure of unfairness is somehow directly connected to the risk, and which is not that surprising, because this is a L2 risk and this is a Wasserstein 2 distance. The good thing about it that, say, risk is measured in squared meters, then unfairness is also measured in squared meters, so we can reason about the trade-off between risk and unfairness. To analyze it, we introduce what we call alpha relative improvement, which is a prediction that minimizes the risk under the constraint that unfairness of a prediction is at most alpha fraction of the unfairness of the base rule. So, for instance, if essentially f star alpha is such that it is 1 over alpha times fairer than f star. If we take alpha 1/2, then f star 1/2 is 2 times fairer than f star. If we set alpha equal to 0, then we recover precisely the optimal fair predictor in the sense of demographic parity. And if we set alpha equal to 1, then f star becomes feasible for this set, and we recover the base optimal prediction. in between, we are starting to interpolate between exactly fair in the sense of demographic parity and just the Bayes optimal prediction. And this interpolation has a very simple form. Essentially, we fix any alpha between 0 and 1, then f star alpha, which is alpha relative improvement, is a convex combination of the Bayes optimal prediction and the optimal fair prediction f star 0. So it admits a very, very simple structure. For instance, you can use a similar estimator. We already know the form of f star 0 from the previous from the previous slides, and f star 1 is just the Bayes optimal prediction, which we also can estimate. The general plugin estimator would also work in this case. But another nice thing that once we derived the exact expression of the alpha relative improvement, we can precisely quantify the risks that are achievable and the unfairnesses that are achievable. We fix any alpha between 0 and 1, then the risk of f star alpha can be measured by the unfairness of the Bayes optimal prediction with some coefficient. And the same holds for the unfairness of f star alpha. It is measured exactly by the unfairness of the Bayes optimal prediction. So there is only one unknown quantity in this formula that describes the whole trade-off of risk and fairness. And you interpolate between the two by one-dimensional parameter in 0, 1. Just to have a simple plot. If, say, we fix some level of UF star, so solid line would be say, high value. Here it's UF star, and here it's UF star. What you can plot is you can plot that how the unfairness changes when we vary an alpha from 0 to 1, and how the risk changes when we vary an alpha from 0 to 1. So unfairness changes in a linear manner. So if we halve unfairness, then it's just half of the unfairness of the Bayes optimal predictor. But at the same time, the risk is not halved. It's a much lower risk compared to the exactly fair prediction, which would be here. Another interpretation of this previous result is through multi-objective optimization. So the global goal is to minimize both unfairness and the risk. Find a prediction that minimizes both. Unless there is some very particular situation, it's impossible, but we can study the Pareto frontier of this multi-objective optimization. Each prediction defines a point in the plane UR, will be the point UF and RF. Some of the points are achievable, some of the points are not achievable by prediction. So this green region is achievable by some prediction, and this is not achievable by any prediction. Then you introduce the notion of dominance. So f is dominated by f prime if risk of f prime is less than risk of f, and unfairness of f prime is less than unfairness of f. And so at least one of these inequalities is strict. So that would be that picture that if you take f star 0, 0, 2, then it dominates the whole region here. And then what we prove is that the family f star alpha is exactly the Pareto frontier of the multi-objective optimization. Pareto frontier are those predictions that are not dominated by anything. None of these functions are dominated by any other function. So, yes, I think just to quickly sum up, regression with demographic parity is intimate relation with the Wasserstein-Barycenters problem. It described a generic post-processing estimator that has a plug-and-play guarantees, and it only needs unlabeled data for the post-processing step. And the last one, I talked about some trade-offs of risk and fairness. using the notion of unfairness that is connected to the Wasserstein-Berry-centered problems. If you want further details, then have a look at these two papers, or especially the second one. There is much more. There is much more information there. Thank you for your attention.
Thank you very much, Evgenii. So again, if anyone wants to ask a question, feel free to just turn on your microphone and speak. So can you just maybe very briefly recall how the Wasserstein distance and actually those Wasserstein-Berry centers show up? I mean, is there an... I mean, with the salaries, for example, with the curves where you compare, you're saying that if in one group you're above 80% of the population, then you want to be above 80% of the whole population. Mm-hmm. That's achieved by this Wasserstein-Berry center. But
yeah.
So is there maybe a deep reason why you want to do this?
Well, a deep reason is kind of maybe locked here because maybe even not here. I will put it. So, what is the Wasserstein distance? Is the minimum over couplings of the expectation of the square difference of random variables. So imagine that this random variable, this random variable lies. If this function f is a decreasing transformation of this function f star, then what you can show is that the Wasserstein distance between the random variables, the random variable f and f star, measures of them, is exactly equal to the expectation of f xs minus f star xs squared. Mm-hmm. The main thing is that in this result, you want to move along the geodesics in the Wasserstein space. And the Wasserstein space pops up only because it is a squared.
Okay.
I don't know if it's clear. Yeah. So essentially, if you take this blue measure and the green measure, and you compute Wasserstein distance between these two, it will be equal precisely to the, and you add the Wasserstein distance between green and orange, it would be precisely the risk of f star 0. You show it.
I understand. Okay. Okay, so I see that on the chat people are saying, I mean, many people are saying thanks for the very interesting talks, and some people are asking for the slides of the presentation. So if Yoon and Evgenii are okay sending us the slides, maybe we can post it on the website. So in the meantime,
I might have
yes.
I might have a further question.
Okay.
Maybe I did not understood very clearly how you do this multi-objective optimization and how you can use it to design this to select actually a very like a fair.
Yes. So
because you have like a what it seems an ensemble of solution with this.
Yes.
And then if you want something which is fair, you would say that you need to be in this Pareto frontier, or I mean, could you explain a bit more?
Yes. So if you measure fairness by this function, rather if you measure unfairness by this function and you measure risk by this function, then what you want to minimize both. Then the only thing I'm saying here is that the only type of prediction that you need to consider are f star alpha that was introduced before, because everything else will be dominated by some of them. For example, this region is dominated by this f star 0, 2. But I'm not saying how to exactly pick one from this curve. It already depends on the actual trade-off that you allow yourself. If you do not allow any relaxation of fairness, then you will be here. So this is the price for the risk that you will pay, but you will not pay anything for unfairness. If you allow some slack, then maybe you are fine to say that I want a prediction that is 2 times more fair than the base rule, which is here. But in this case, I want the one that has the lowest risk, so it would be this point. But I'm not given a recipe how to precisely select 1 point from this curve.
Okay, so what you're saying is just like if you want something which is like kind of achieve the right trade-off between these two, you have to be better. But does it, in a sense, can it be compared to with like some kind of ideas with a regularization where you have this regularization parameter that interpole a bit between like a full regularization and no regularization at all? So is this is the like 0.2 parameter like correspond kind of in a sense to this?
Yes, this is the kind of the, well, it does correspond to something, but I don't know if this connection is explicit, but it's kind of the relation between the constraint problems and the penalized problems. A lot of times you can find an explicit relation one direction, but you cannot find the other. Here we did not try to find the exact relation with the penalized version. In a way, this alpha relative improvement is a way to study this multi-objective optimization.
And is it complicated to compute this? Oh no, this was with the Wasserstein. Okay, yeah. I get it. All right, thank you very much for the answer.